All right, good morning, everybody. I'm glad to be here with you. My name is John Stewart, and I'm going to be talking about the Next Generation Liquefaction, or NGL, project, with the focus on work we've done over the last few years on the development of triggering and manifestation models. I want to acknowledge the folks who've worked with me on this. Pictured on the top, Ken Hudson. A lot of this work was in his PhD thesis from the end of 2023. Kristen Ulmer at Southwest Research Institute. Paolo Zimro is associate professor in Italy, former postdoc, and Scott Brandenburg and Steve Kramer. Before I move on from that slide, I do want to also acknowledge the many sponsors of this work over the years. Most of the work I'll talk about here today was funded by the Nuclear Regulatory Commission and the Bureau of Reclamation. NGL was born here at the Pierre Center a little over 10 years ago, and the vision for it was fairly simple but revolutionary within the liquefaction field. And that was to develop a community database that all the different model developers for different liquefaction models could contribute to and then use in their work, and that we would have models that come out of that process that are probabilistic, developed in a transparent way, and users could have confidence in their implementation. That vision was strongly reinforced by the National Research Council in the report you see here on the right, that this is really what the profession needed to move forward. That report originally came out in 2016. So the project as a whole has elements of database development, what we call supporting studies, which are to provide knowledge on issues that can't be constrained necessarily from field case histories in our database, and then of course the development of models. The image on the right is a screenshot of the database, which is, as Dave just described, a living database. We had a very concentrated effort to develop this, but we are still improving it and adding new data to it. And NGL is also a pretty large community of liquefaction researchers. I won't take the time to go through all these different boxes here. I'll just point out that where I probably mostly sit is there in the project management team, along with Steve Kramer and John Stamatikos. We have many different model development teams, that's on the right, and then at the bottom there's folks who have developed the database and have done different problem-focused studies. So the focus of my talk today is going to be on the model development part of this, and I want to just start by highlighting a few features of this effort that really make it different than what has come before. There's some unique opportunities that are largely enabled by the database. So there are more case histories than has ever been present before. In modern case histories, there's a lot more data per case, and it is possible now, because this is in the cloud and it is a relational database with a very systematic structure, you don't need to have all the data on your PC. You can basically perform the necessary calculations very efficiently compared to how this used to be. It's always been the vision that the liquefaction models would be fully probabilistic and that we would define our knowledge-based limitations, epistemic uncertainties, and we would define aleatory variabilities which reflect the natural variability in the data. It's always important to do this. Geotechnical engineering, as many of you know, is a highly uncertain field. That's just the way it is, and we need to quantify it. Ground motions, this won't be the focus of my talk, but this was a pretty major effort to try to resample the ground motions from all the different case history sites in a way that honors the recordings of those earthquakes when they're available, and also aligns with what is actually done in forward applications to predict ground motions when the earthquake hasn't happened yet. And another aspect of this that I think when we first started NGL over 10 years ago, this wasn't so much on our radar screen, but it quickly did become, which is that what happens to a profile when it is strongly shaken by an earthquake is sometimes fairly simple, but it's often not so simple. And there's this complex profile system behavior that can take place that controls whether you actually see effects of liquefaction or not. Misko Kubernovsky in New Zealand has been a leader in this area, and we've tried to integrate some of those lessons into the model development. It's important in liquefaction to recognize that it's kind of a three-headed monster. There's three phases, one builds upon the next, and they have to have very specific definitions, both for the model development and just to clearly communicate what we're doing. The word susceptibility here talks about the potential of a soil to experience liquefaction, strength loss, etc., and it's taken as a fundamental material characteristic. So if you have a sandy soil that is well above the water table in Kansas, okay, it's susceptible, okay, because it's a fundamental material characteristic. Triggering is where we evaluate whether a given susceptible soil is likely to actually experience this strength loss, depending on whether it's saturated and what is the strength of the shaking, and of course information about its state. So that soil in Kansas that's not saturated and won't see strong shaking would not trigger, but it would be susceptible according to these definitions. And then manifestation is where you basically try to look at the different layers within a profile and decide whether you're going to see the effects of liquefaction up at the ground surface. That could be boils that come up, could be instabilities, a whole host of different things. And that's a really important part of this because that's where the infrastructure often is, and that's also where our observations are when we go out and we observe the effects of liquefaction or the lack thereof after earthquakes. So just to reinforce that latter point, the observed field performance, there's a strong empirical basis to what we're doing. We're observing what happens, and that observed field performance is of manifestation. And that's an important point because it's often been equated to triggering, but it's really an observation of manifestation or, of course, the lack of manifestation. And we need to deal with that in the model development process. So I'm going to go through these 4 steps quickly so you can kind of get a sense of how we came up with these models. There's a Bayesian approach here. We have a triggering prior, that's probability of triggering given susceptibility. I'll spend some time on the manifestation models, which are derived from case histories. And then in the process of developing that manifestation model, we update the triggering prior. So to help understand some of our thinking here, I'm going to go through 3 kind of hypothetical cases. This first one, manifestation is observed. We have a shallow groundwater table with very loose soil underneath it. So it's a thin crust and it's a thick susceptible layer. In this layer, the probability of triggering given a strong earthquake would be very high given the looseness of the soil, and the probability of manifestation given triggering would also be very high. So the product of those two means we expect to see manifestation as observed. In the second case, we don't see any manifestation. We have, again, a shallow groundwater table, but we have very dense soil beneath that water table. So it's a thin crust and a thick susceptible soil. The probability of triggering in this kind of material is going to be very low, but the probability of manifestation, if triggering were to happen, would be high because it's shallow. Nonetheless, the product is low, so we don't expect manifestation, and conversely, we do expect no manifestation. So this would be a case where we would probably anticipate the performance that was observed. But then we have a lot of cases like this third one here, where we have a moderately deep water table and kind of a medium dense sandy material underneath there. So both are kind of intermediate cases. The corresponding probabilities are also intermediate, and we would have an intermediate expectation of whether manifestation might occur or not. And it didn't in this case. So then the question is, why did it not happen? Did it not liquefy because the soil was too dense and it never triggered? Or did it not manifest because maybe it did trigger, but it was suppressed in its manifestation due to the thickness of the overlying materials? These are the things we have to unpack to develop a rational model. Now, if we look at these 3 examples in the context of kind of traditional legacy-based models, they are formulated, as you see on the right, a strength of shaking on y-axis and a penetration resistance on the x-axis with a boundary line in between, which is often taken as the strength of the soil. So that first case would be, as shown here by number 1, we observed manifestation, it's above the curve, that is a true positive. The second case, we're below the curve, manifestation did not occur, it's a true negative. And the third case could very well plot above the curve, but it shouldn't be above the curve. It's supposed to be above the curve should be a case with manifestation. This one did not have it, so that's a false positive. And as it turns out, as you objectively look at all of these different case histories, there's a lot of these false positives with the current legacy models. And oftentimes that's because of this correlation or relationship between manifestation and triggering. The approach that we have is a Bayesian approach. We see Bayes' theorem here. We're trying to predict, among other things, the probability of triggering given manifestation, which is the probability of manifestation given triggering, probability of triggering divided by probability of manifestation. We can unpack that probability of manifestation term in the denominator given the two possibilities, either it triggered, so probability of manifestation given triggering, or probability of manifestation given no triggering. And this is essentially the framework within we're working to develop models. We need three probabilities to do this. We need a probability of manifestation if triggering happens in a layer. We need a probability of manifestation if triggering does not happen in a layer. And the collection of these two are probabilistic manifestation models. We also need a probability of triggering initially before we go through this empirical Bayesian analysis, and that's called a prior probability for whether we think triggering is likely to happen in a given layer. So we're doing this in a different way. We're not doing a critical layer where we kind of focus on one layer that we think is the most important one, because it's often very difficult to select those layers. Instead, we're doing a profile-based approach. What we're looking at on the right is a CPT profile with QC1NCS is like a density of the soil representation, and I sub C is a soil type 1. And the red line there is a representation of that profile developed through this automated discretization procedure available at NGL Tools. And then what we do is we basically go through the profile layer by layer. We evaluate susceptibility and triggering for each one. And then the manifestation is assessed based on the overall profile, not just a single critical layer. Now the triggering prior, I won't spend much time on this because of time limitations here. I'll just point out that this triggering prior is a relationship based on available laboratory tests. We developed a large database. We expanded the NGL database to accommodate this. So it's a database of lab tests now. We developed this database. They come from triaxial tests and simple shear tests and all manner of different kinds of samples. And after a lot of consultation and thought, we decided to come up with a relationship that represented a particular set of that, which is intact samples, so not remolded samples, and simple shear testing, which best corresponds to field stress paths. Points that don't have those conditions, we came up with empirical adjustments for them in order to approximate that condition, and the resulting relationship with its uncertainties is on the right. CRR, which is strength, versus the density of the soil. So here's where I'll spend most of the remaining time, manifestation models derived from case histories. So I'm going to kind of walk you through how this works, because this is really something very new for the profession. It's derived from case history data. So this is where the case histories come in. Remember, the triggering is based on lab testing. The manifestation is where we use the case histories. One part of that process is a layer-based manifestation model, which you can see it here on the bottom. The y-axis is essentially the probability of manifestation of a layer. The x is one of the controlling variables, the depth to the top of that layer, and the different contours are different soil types, basically, as represented by I sub C. So what I'm going to kind of walk you through here is how the use of this operates to assess a profile. We're going to consider a 3-layer profile. You can see the top one is fairly dense, high QC1N, but it's also fairly high fines content and maybe somewhat plastic fines represented by high IC. As we go down to the green one, the soil gets looser, but it remains with that high fines content, high IC material. And then below that, we have a looser soil and one that would be more susceptible in yellow. So we're going to move that down to the left, and we're going to walk through each of these layers. So we have the probability of manifestation given triggering that we're going to look at first for the red layer. And looks like I've had some jumbling of an equation here, but what that's basically telling us is that the model that I showed you before, which is supposed to be showing up on the right side, is going to give you, in terms of the depth part of it, a very high probability. but then this part is working better. It has an IC component as well. Because the IC is fairly high in this case, that's going to bring this probability down. And so in aggregate, we're going to have about an 0.3 as you see circled there. Then there's a triggering probability because this is a high QC1NCS material and also a high IC. That's a fairly low number. And so the product, 0.3, 0.2 is 0.06. We don't have a very high probability of that layer manifesting, even though it's right next to the surface. So we go down one, we're a little deeper, and we're still high IC, so the probability of that layer manifesting is quite low. The probability of triggering in that layer is fairly modest, and the probability of manifestation of the layer is very low, 0.04. Now the yellow layer, this is the one that is both sand-like and fairly loose. The probability of manifestation in this case, as you see by the yellow dot, is fairly high at 0.5. The probability of triggering might be about 0.8, fairly high because of those conditions. The product gives us 0.4. So then we look at the profile now, given those results for individual layers, and what we have here is a product sum of the complements of layer manifestation, as you see in the equation on the bottom. Essentially, we're taking 1 minus the probability of no manifestation products for each layer, and you end up with 0.46. So that's how all the different layers are brought together. In this case, it's mostly controlled by that bottom layer, but they all contribute something. By using this kind of a framework where all the different layers are considered, if we compare what we get with this framework to legacy models that are based on critical layers, we get quite a bit better representation of the case histories, mostly because a lot of those false positives are no longer false positives. As part of the Bayesian updating, the lab-based triggering relationship is also updated based on the data. So that's an outcome of the Bayesian updating process, and we basically go from the red curve, that's the lab prior, down to the black curve. Although the change is fairly modest, it is actually still within the error bounds of the original laboratory curve. This whole process is influenced by various model components, including fines corrections that we have made based on information from literature. And so it's important to note that as we move into the conclusions. So the main point I want to make here in connection with the modeling is we've tried to rigorously unpack triggering, which is often what we're trying to calculate, from what the database actually contains, which is information on manifestation. What Peer and others are actively supporting right now is improving our susceptibility models and also the fines corrections that are integral to this whole process, which may shift some of these models around as those downstream models come online in the coming months and years. And I'll just point out the advantages of this framework, which is very new, is we are defining uncertainties. Everything's probabilistic. We are aligning the calibration process with the actual data that is observed, which is field performance. And it is well suited because we are seeing what happens in each layer within the profile to liquefaction effects analysis, where you might be very interested, for example, in whether a layer deep in the ground that is the bearing layer for a pile is liquefying or not. Traditional models can't really give you that. So in terms of references, the QR code on the right will take you to the NGL database. The URL is also there. The NGL tools for performing a lot of these calculations is a DOI given there. I want to mention that there is a webinar, no, sorry, not a webinar, a workshop, an in-person workshop that ERI is hosting in Oakland at Dayton Culp's office on May 17th, and registration is open for that. And in that meeting, we're going to take a much deeper dive into all the different steps here in our model development process and how to use them. And these are the different references that I've cited. The one on the bottom is the NRC report that contains all of these model components and the justification for them. That does it for me. Thank you.